Good morning, everyone. Still some folks joining. Great. So when I entered this room this morning, like an hour ago or a bit more, I noticed this room was very warm. It's also warm outside, but also very warm in here. And also a while ago, so I'm from the Netherlands, and we also had a heat wave a while ago, and my children were complaining that their room was very hot. Can you do something? They asked me. I said, sure, I can do something, but wait, I'm an engineer, so I have to measure first. I'm not jumping into any action, so I'll measure first. So I bought some temperature sensors to measure the room temperature in their rooms and hooked that up to Home Assistant, which is a home automation platform. And then my kids could see how warm their room was. And they started comparing their room temperatures, and that kind of already solved the problem because they could complain, I have the hottest room, it's the worst for me. So they were happy or happy enough, so I didn't need to take any action. But I had these temperature sensors anyway, and I had the data from these sensors. So I thought maybe I can play around with it, do some coding kata with that sensor data, and see what I can get. So I used Java streams to process that data. But at some point, I didn't have enough tools in the Java streams to do what I wanted. And then a couple of months ago, Java 24 came out, which had the gatherers. And that's what we're going to talk about today, the gatherers. So quickly, who am I? I'm Hinse Schuur. I'm from the Netherlands. I've over 20 years experience, mostly with Java, but also some Scala experience, and I worked in different industries as a consultant. But enough about me, and let's talk about Java streams. So I assume that everyone in the room here uses Java streams in one way or another. Who is not using Java streams? 1, 2, 3. Okay, 3 people. So who's on a Java version before they could use streams? So those are not those people. Okay. People already on Java 24? No? Great. So we'll learn something new today, I guess. So why we love Java streams? So the Java streams were introduced in Java 8, which came out 11 years ago or so. And these streams allow you to have nice chains of transformation. So you only need to think about a small transformation, and you can chain them together in a stream. And that also makes them a nice fit for lambdas, which were also introduced in Java 8. So there was a nice combination to have those. The good thing with Java streams is they are computed lazily. So as opposed to, for example, a Java list, if you want to transform a list, you always need to go through all the elements, while with the streams you can do a map, and until you reach the final operator, the data is not computed yet. So that's different. And that allows for potentially unbounded streams. So you can have streams that can go on forever. And also nice when the streams were introduced in Java 8 that they were easy to parallelize. You just ask for a parallel stream and it's all magic, it all works. At least that was what we learned then, so that was good. So what is actually a stream pipeline? So a stream pipeline consists mainly of 3 main components. So you have the source of elements, where the elements are coming from. Then you can have any number of intermediate operations. It can also be 0, but typically you have some intermediate operations like filter, map, flat map, limit, all those kind of things. And then at the end you have a terminal operation, and only one terminal operation. And I have to admit that sometimes when I was coding, I forgot about the terminal operation, and I was wondering, why didn't I see any output? Any other people who forgot about the terminal operation at some point? So quite a few, good. So we're in good company. But that terminal operations also triggers the stream to be materialized, kind of. So as soon as you hit that terminal operation, then it starts consuming the elements, pulling them from the source, through the intermediate operations to the terminal operation. And you can only use a stream once. So once the terminal operation is called, you cannot reuse that stream again. So if we have a quick look at how the streams look. So there were 3 people who don't use streams yet. Let's see. So here's a small example. So this measurements, it's an example function that provides a stream and it's example data. So I kind of emulated the sensor data from temperature sensors. And in this case, I tweaked it a little bit so that we get a data point for every minute. So we get temperature and the sensor ID for every minute. And then, so we will be using this in all the examples, this measurements thing. And if we look at the stream, so the measurement are records and they have a timestamp, temperature, and a sensor ID. But we will be mostly looking at temperature and for some examples at the timestamp as well. So when we normally run a stream, so this is the source where we get the stream. You also see here it says a stream of measurements. And then we can filter it, so filter out all the temperatures above 20. And then we map all the elements to a nice description, so a format method. And then we limit this stream because this stream is unbounded, so it will produce endless measurements. Then we limit it to 50 elements, and then we do the terminal operation. So for each of the elements, we print them. So if we run this, we will see the data in here, and it formats all the measurements nicely. So timestamp and temperature and the sensor ID. What's also interesting to know is when you debug these streams, and this is something I learned when playing around with the getters, you can put a breakpoint at any point in a stream. You run the debug, and then you have this option here in the debug, which says trace current stream chain. And that will show you the elements, how they flow through the stream. So it's a very handy feature in IntelliJ. So here it shows the source. So here you see all the measurements. And then you see what happens with the filter. So you see those first elements didn't pass the filter. And you have them on the right. And you can also inspect the elements. And you can also view then the next step. So it was filtered first and then mapped. So you can also see from a measurement object, it went to a string. You can also view that string if you want. And then the limit and the for each. So this is in presentation mode, so it's a bit bigger than you normally would have on your screen probably, but on a bigger screen or in a different resolution, you could also use the flat mode where you can view the pipeline in one view. So this could help sometimes with debugging streams, so that's probably good to know. So that's for the first example of what streams are. So that's all good. So I could do some useful stuff with this temperature data, but then I run into some issues. So I was missing some functionality in the streams that wasn't provided by default. And there were actually, of course, more people complaining about, hey, I want to have this specific operation. For example, I would like, next to a map, I would like to have a fixed window function on a stream, for example. But that doesn't exist. Or maybe people wanted to have a zip width index, which could be similar to something you have in Kotlin, but it also doesn't exist. So the JDK people thought about, we can introduce all those separate methods, but not sure who's going to use what. So let's invent a generic mechanism. And that generic mechanism for intermediate operations was the gatherers. So it's available since Java 24. It was already in preview on Java 23 and I think also on 22. So if you want to read about it, a bit more about the design, you can check the JDK enhancement proposal 485, which is actually a nice read and not too complex. It's not like reading a full specification, so it's a good read. But the gather mechanism is you call the gather function on a stream, and then you provide it a gatherer. And this is heavily inspired. Some people might recognize something that it looks very similar to collectors, which you have at the end. So previously you didn't have the toList, for example, on a stream. You had a collect, which you could use with a collectors toList or something. So this is quite similar to that collectors setup. And the nice thing, and I think it's also like required for these gatherers to be useful in every situation, that they support parallel streams. So that's one, that they can do lazy evaluation. because that's the whole idea behind the streams. The interesting thing here is that they can use state, which is without gatherers, it's not really doable in streams to keep some state in between the steps. So that's actually what the gatherers make very special and make them very useful. And with these gatherers, you can do all kinds of transformations, like one-on-one or one-to-n, or you can group elements into one element, or a bunch of elements into one, and then the next bunch into one. So basically, you can do n-to-m transformations, as we will see later. So then going back to my temperature data. So I had this temperature data, so it's all a lot of data points. It's very jaggy. There's a lot of data in here. You don't need to read the data, of course. It's not, the details are not important on this one. So it's like a couple of hours, like 24 hours here plotted. And I wanted to have an average temperature per hour. So on the right, we see the average temperature per hour. So I see at 6 o'clock, like the average was this. At 7 o'clock, the average was that. So you need to calculate that in a way. But with the normal streams without the gatherers, you couldn't do it. But now with the new gatherers, there are 5 default gatherers, and one of them is the window fixed. So that will provide you a fixed window concept. And what's a fixed window? So it will basically go through your stream. So these are the elements in the stream representing temperature data. And then in this example, in orange, I'm showing a window of 3. So I'm looking at 3 elements each time. So for the first, after 3 elements, it emits one window, one list of temperatures, in this case, or one list of elements containing 3 elements. And then the next element will also be a list containing the next 3 elements. And then for the final one, there's only one element left. And then you will get that in a list. So you have a list of one item. So it will go so the window jumps basically to the next window. So if we see this in an example, let's have a look at if we want to calculate the average temperature per hour. We can do that using the getter. So you start with using the getter. So what I have here, by the way, so I still have the measurements, of course. With the map, I extract the temperature. And then here I want to calculate the average in some way. So what I can do is use the gatherers. So the default gather, the window fixed. And then in this case, I would like to have 60 elements, so 60 minutes. I want to have a window of 60 minutes. And then here you can see that you get out a stream which has lists of double. So those are the temperatures in a list. So a list of 60, and then so it continues. And in order to calculate an average, you still need to do something with that window, with that list. So you can map that to, for example, calculate the average. So I have a utility function to calculate an average of that window. And I get the data. So when we run this, so you have to trust me, these are the average temperatures, like for the first hour, for the next hour, for the next hour, and then we have this 24 times. But if we look at this in the debug view, then it maybe becomes even more clear. So if we start the debug on this, so it breaks on the stream, and then we use the trace current stream chain again. Let's go for the split mode. And then here we see we have the gather. So it doesn't really know the relation between the input elements and the output elements because it's collecting them first. So you see here collections. So these are the windows on the right. And those have 60 elements. So that's one window. And then here we see the next window, which has 60 temperature elements. So this is how the fixed window works. Let's run the example. Okay. And then it was all nice. I had the temperatures per hour. but I was also looking at how the temperature changed over time. So I was looking at, let's say, this is an hour of data, or actually 2 hours of data. But as you can see, the orange line is jumping up and down, and it was a really jaggy graph. So I wanted to smooth that out. And what you can do is using a running average. So you can calculate the average of the previous 3 data points, and then the previous 3 data points. And if you calculate that average, for example, 3, you could also use 5, then it will smooth it out. So that's what happened with the blue line. So on every point, it calculates the average of the previous, so the current element and the previous ones. So in this case, it was a running average of 5 elements. So if you want to use that with the default gatherers, you can use the window sliding, which is quite similar to the fixed window we saw, or the window fixed we saw before. But in this case, the window doesn't jump a whole window further, but it slides across. So for the first thing, it emits a list with 3 elements, the first 3, and then for the next element that comes out is those 3 elements, like 3. So it slides over your stream until it reaches the end, and then you have the final sliding window, which also contains 3 elements. So in this case, they're all with 3 elements. So if we see this in action in code, so this will actually look quite similar. If we look at the third example, so in this case, is it readable on the back, by the way? I see nodding heads and a thumbs up, so that's good. So again, we start with the gather, because that's how you use the gatherers, and then you can use the built-in ones, which are the gatherers dot window sliding, and we want to have a 5-minute sliding window, and then again, we need, based on that window, we need to calculate the average. So here we see also it emits lists of doubles. So if we run this, we will also see the average temperatures, but then for every 5 minutes, basically, and it slides. So you get the smooth graph like I showed you before. All clear so far? Good. And then I was also thinking, I want to see the average temperature like over the whole period. So I want to calculate not every individual point, but I want to calculate the average. But I also want to see how the average evolves over time. So what I did, at every point, I calculate the average of all the previous elements. So the current element and all the previous ones. So at some point, this should, I don't know, be a horizontal line if it's the temperature always, like, if you have the average of a really big amount of numbers, it will be a straight line at some point, I guess, but it was not at this point. But if you want to calculate this, you can use something like the scan default gatherer, which can help with this. So what the scan actually does, when you use the default scan gatherer, you give it a starting element. In this case, let me zoom in a little bit. So a starting element. So in this case, I want to add up the temperatures for this small example. So if I want to add up temperatures, I start with a 0, and then that's provided to a function that you give it, and then it combines it with the element. So you have the starting element, it combines it with the operator you define with the element. So it does 0 plus 20 is 20. And then for the next step, it takes the previous calculated value, it uses that as input, and use the operator here, and then combine it with that element. So in this case, it will be 20 plus 20.5, resulting in 40.5. And so it continues. So every time it provides the previous element or the previous calculated value and the next element from the stream. So then it goes through the whole stream like this. If there is no element in the stream, you will get no data at the downstream. And there's something similar, which is the fold. So it's very similar to the scan. The big difference is that it doesn't emit the intermediate values to the downstream. So if you call this fold gatherer, you won't see this element. While in the previous one, you would see the 20, you would see the 40.5 coming out, you would see the 61 coming out. With the fold, you don't see it. only until the last element, then it will only emit one element, and that's that final element. That's, in this case, 1 of 44. So this is very similar to what we already had, which was the reduce operator, which you had as a terminal operator. So this is basically kind of the reduce, but then as an intermediate operation. If we check this in an example, then we would do example 4, where we could calculate the average. And in order to calculate an average, I need to keep a total count and so I need a total and a count. Let's call it stats, and let's have a count and a sum. So that's something I need to keep track of some state if I want to calculate an average. So again, I use the getter, and then gatherers dot scan, because that was what we want to use to see the average. And then it requires some arguments. So it's the initial value, or a supplier for the initial value, and a function to combine it, as we saw in the slides before. So we start with initial value. So initially, if we want to go through that stream, we want to start with a new stats object which has 0 elements and has a sum of 0, like this. And we also need to provide a function which combines a stats and the next element coming from that stream. So in this case, we would have the previous stats, an element, and then you have to return a new stats in this case, and give that the stats.count plus 1. So we're having a new element, and we have to add the sum, the element to the sum, like this. And then we get a stream of stats object. So we get that if we go back to this one, we would see basically this happening. So if we run this, we would print out the data, we would see it counting indeed, and we had the sum. It's still not an average, but that's not too hard, because we can use like normal map function, which we already had on streams. So we get a stats object, and we calculate the average by dividing the sum by the count. So in this case, we get an average, basically a cumulative average, so that you see how the average evolves over time. And if you want to turn this into like the fold I showed, that's a bit too much. If we want to use the fold, then you would see that we will only get one element instead of all the elements. So if we run this again, we would only get the final element, the 90.025. So we had 4 default gatherers, and then there's one more. It's called the map concurrent, and it's kind of similar to the map we already had on streams, but it does it concurrent, of course. And it's using virtual threads for that. And the nice thing is that you can specify how much concurrency you want. So with parallel, you don't have, so if you want to do something with parallel, you don't really have control over how much concurrent things you want to use, and it's not backed by virtual threads, while this one is by default. So you can basically map every element and, for example, do calls to a REST service or a database. Not saying that's the best design, that you should do a call for every element, but you could do it with this. And the nice thing about this is that it also keeps the order intact. So it starts, if I use max concurrency 3 in this case, when it sees the 3 first elements, it starts to provide those elements to the mapping function concurrently. And as soon as the first one returns, it emits that item to the downstream. And it could happen that not the second element gets mapped first, but the third. Then it will kind of remember that element, but won't push it downstream. So it will keep the order. So as soon as the second element is produced by the mapping function, it will emit that to your downstream stream, or the downstream stage. And it will also emit that third, which it remembered. So it ensures that all the elements are mapped in order. So if you have the source elements in a certain order. At the end, you would see the mapped values in that exact same order. That's the beauty of it. So if we see this in a live demo part, then it would look something like this. So here I have still the measurements, and suppose I want to combine the measurements I have with the outside weather at that timestamp. So I could call a weather service to get the data at that time. So that's what we're doing here. So I'm going through all the measurements, and then if I get a measurement, I call the weather service at this particular timestamp. This is probably not the best design if you have like 1,000 elements to hammer that weather service and call it 1,000 times in a row, or maybe some stuff in parallel, because I added parallel here. So this is like how you would do it before. But if you want to use the default map concurrent getter, you could use it like this. And what you specify first is the max concurrency. So it will ensure that even if it's parallel in the stream before, that it only send out a maximum, or have, how do you say it? Have exact maximum that amount of mapping functions running. So you won't overload, for example, a downstream if you're calling a server. So let's say we do have a max concurrency of 30. And then, like with the previous, like the original map, you can just use the same lambda to do the mapping. So this is equivalent of what we had before, but now it's map concurrent 30. And then we would see the data here. And you saw it waited for a bit. That might be a bit confusing. Because it's parallel, and it seemed to wait before all the data was in. That's caused by the parallel, because the getter here had to wait before the parallel thing was completed, was fully completed, in order to keep the order of elements. So if you remove the parallel, which I think in this case is better, because then it doesn't need to wait for the parallel section to finish. It can just start mapping items right away. And then you would see them being emitted on the go. And we would see 30 each time, basically. And you can, of course, play around with this max concurrency. So these were the default gatherers. But yeah, these might not be sufficient, because there are only 5, and there might be more use cases than windowing and scanning and mapping. And luckily, you can roll your own getter, like you can do with collectors. So let's see whether we can implement our own getter, so one of them. Let me first introduce some concepts. So an important concept is the downstream. It's an interface you don't need to implement. It's provided to you by Java, actually, and when you run the stream, it will provide you the correct downstream. It represents, of course, the downstream stage. So you can push elements to a downstream, and it will give back whether it wants to have more items. So if it returns true, it wants to have more items. And you can imagine if you have a limit downstream, at some point it will say, no, I don't want to have more items. And then you can shortcut in some way. So you can stop pushing stuff. But you can also ask it beforehand whether it's already rejecting elements. So then you can optimize things in your getter if you want to. But normally you would only, or in most cases that I've seen, you only use the push method to just push elements downstream. And then the getter, so be warned, there are some generics in here. So it looks a bit intimidating to some maybe, but it's actually not that hard. So the getter interface, which you also rarely implement, I think, unless you do something very specific. So there are some helpers that help you implement getters in a simpler way. But I think it's good to see the stripped down version. So a getter, so it has the T, that's the input type of elements. We have the A, which stands for the type of the state, so that it can make sure that it knows what type the state is, and you will see the state in some of these methods as well. And the R is the resulting type. So you have the input type T, the resulting type R, and then the A for the state. And as soon as a getter is kicked off, and that's when a stream gets processed. So if you call the terminal operation, then the stream framework starts to work. And then when it sees a getter, it starts by initializing a state. So it initializes a state by calling the initializer, of course. So it says, give me a mutable state, and that's the important part. So you can actually mutate state, and the stream framework will take care of that. So you provide a way of creating a new state, and then you say something about how you integrate new elements, T, given a state, and then of a given return type. So most of the time for gatherers, and also the getter is a functional interface, if I'm not mistaken, this integrator is the main thing that you need to implement. You cannot have a getter without an integrator, but you can have gatherers without state, for example, or you can have gatherers without a finisher. And talking about a finisher, finisher is called at the end. So when all the elements were provided, and then it says, okay, there are no more elements. If you want to do something final, you can do it now. You can push some more elements to your downstream if you want to. So this is very useful, for example, in the fixed window and sliding window things. So with the fixed window, it could happen that it had like 60 elements, and then for the last bit, it only got 3 elements. So it stored that somewhere in its states in a list, and then stream is over. So then the fixed window could use that finisher to say, I still have 3 elements. I push those as the final window to the downstream. So that's what you can use a finisher for. So it all depends on what type of getter you want to implement, whether the finisher is relevant. But for stuff like Windows, you would definitely need it. And if you want to really support parallel streams, so you can, by default, it's easier to go for sequential streams, like non-parallel. But if you go for parallel support, then you also need to provide a combiner, which basically combines 2 states. So if you have like a parallel stream, which is divided into, let's say, 4 streams of data, or 4 groups of data, then it calls the state for that first group, and also it creates a state also for the second. Then it starts processing with the integrator. At some point, it combines those states with the combiner until you have finally one state, and then it can use that and use the finisher on that one as well. But I'm not going too much into detail for the parallel support, because that's probably a bit too much for now. And then there's also, so the interface for the integrator, this is also a functional interface, which says integrate an element given the state, an element, and a downstream. So it doesn't, you don't have to return an element, but you push it to a downstream. So you can push multiple things, or one or none, you could choose. So this is all theory. And then, as I mentioned before, there are helper methods to make it a bit easier to get started with implementing a getter. So the first thing you want to think about when you create a getter, whether it will support parallel streams, or whether you want it to work in parallel, or whether it can be sequential or has to be sequential. So the sequential is the easier way, I would say, but less powerful if you use parallel streams a lot. So you specify that it's a sequential thing, and then at least you specify an integrator, and that can be just a lambda if you want to. And if you don't specify an initializer, then it assumes a void state. So there's not really any useful state. You can also use an integrator and a finisher. Still, you don't have any state, but you can emit a final element which is not based on state. Not sure what it could be. I can't think of something at the moment, but there are probably use cases that it's useful. And you can also provide all the 3 things, like the initializer, the integrator, and the finisher. So in this case, this is a very powerful getter, but you also have to provide quite a lot, and these can all be lambdas if you want to. Doesn't have to be. So this is for the sequential, and Then if you want to have parallel support, you have to provide the combiner. So we basically see the same methods. The only difference is that it's not called off sequential, but it's off. And then if you have state, you need to provide the combiner function as well. So this is for the theory. So it would be nice to see something in action. We could think about multiple examples, but let's go for the zip with index, which I showed before, because that has some state. So what I want to achieve with the zip with index, suppose I have a stream of elements, I filter something based on, for example, the temperature, then I don't have the index anymore, right? If you go through a stream, there's no such a notion of index, but suppose you want to combine it because you want to print out first element, this, next element, that, but only the things that match those, this filter. So we could implement something like zip with index, which could be our own gatherer, and it would accept a function which gets the index and gets the value of that element. And then we can combine it in some way. So we want to do something like this. And I already created a helper method, and this is what you see a lot when people create their own gatherer. They implement a factory method, so a static method, which has a gatherer which returns the correct types. But almost always they use a question mark like a wildcard type for the state, because you don't want to communicate to others what the internal state is, because it's really meant to be internal. So internally you want to know what the type of the state is, but to the outside world it should not be relevant. So for the zip with index, so it's I would say sequential by nature, because you have to keep an index. So we start with a gatherer.off sequential, and then we need some state. And the state is, in this case, is very simple. So it's just an index where we are in the stream. So we can create a very hidden class, let's say. So we can implement it just in this function, which you also see a lot in examples of custom gatherers, that they implement the state very local, so you cannot use it anywhere basically. So even if it leaked out, you couldn't use it in some way. And it will only have a count. You can make it 0. And then for the sequential thing, we want to implement a gatherer, and then the first thing we need to implement is the initializer. So we need to initialize our state. When it starts processing, it needs to create the state. So what we do when the gatherer starts, we want to create a new state. We can modify this state if we want in the integrator. So that's the next step, implementing the integrator. And an integrator is basically it has a state. It gets the state. So I'm using a lambda here because that's very short. It gets the state and the element being pushed to it, and you can use the downstream to send your resulting items to. So in this case, we want to probably and we have this function that we got. That's the thing that does something useful with the index and the element. So we probably need to use that. So what we could do is the transformed element or something, and do something like we want to call the zipper with that thing from the state. So we check the state and we increase the count, and we also get the count, of course. Oh, it should be called apply like this. And we should give it the element, which we already got from the as part of the integrator. So now we have a new element, which is a transformed element, and then we can push that thing downstream. Push, and we push that transformed element. So far it's going well, but now it complains that we need to return something. So as an integrator, you also need to specify whether you want to have more items. But in this case, we don't care whether, so we don't have an opinion on whether we want more items. For us, it's fine. So we just return the value that was returned from our downstream. So as long as our downstream wants more elements, we also want more elements. But if you want a shortcut at some point, let's say you want to do a max number of elements, you could also check here, okay, we reached the max number of elements and then return a false. That could also work. So this basically is a getter. Maybe it's not the most beautiful to have a two-line lambda in here. So there are some people who don't like multi-line lambdas, but you can always extract this to a method or implement something on the state that could help you with this. And if you run this, we would see that we get exactly like the index with the string, and we can, if we want, we can change the zipper function here. So we have a function which gets the index and the value and can do something fun with it. So I can imagine that things like these end up in shared libraries, which provide some additional default getters. Maybe something like this ends up in the default getters later in Java. I don't think there are new getters scheduled for Java 25, but yeah, I can imagine that these pop up at some point in time. And of course, there can be more ideas for custom gatherers. So you can think of things like segment by or window by. So in my example, I used measurements which came out every minute. So every 60 seconds there was an entry. But in reality, these temperature sensors only send data when the data changed. So I don't get data every minute. So if I want to do an average per hour, I need to segment by the hour, let's say. And that's something that's not built in. You can only say every 60 elements. But you could implement something like a segment by or window by, which you provide a function saying, hey, provide segments or windows by this specific property. And then you could have basically the same thing, but then for like the real sensor data in this case. You could think of if you see an element which is twice in a row, you could only emit one of them. So if you don't want to have duplicates, you could implement something like collapse consecutive. You only need to remember the previous item. It's not that hard to implement, but it might be fun to try if you want to try some gatherers. A distinct by, which you could use because currently in Java streams, there's only the distinct. But I can imagine that you want to have distinct by a specific property, which you could also implement. And there are more things that you can think of as implementing for gatherers. So what did we gather today? So gatherers are like collectors, but then for the intermediate operations, there are 5 default ones, 2 for the windowing. We have a scan and a fold, which are quite similar. And we have the map concurrent, which can be very useful. And if you want to implement your own gather, so prefer the factory methods first to create your own gatherers, but also the gather off and gather off sequential. Use those in combination with some lambdas that will get you started pretty quick. Hide the internal state, like I mentioned, with the question mark, so don't leak your internal state to callers of your gather. And if you're starting out implementing your own gather, please start with the sequential. You can always add the support for parallel later on. So I would say only do that when necessary, because it adds complexity, which is not always needed. So having said that, I started out with the temperature. I didn't really solve the issue of the temperature in my kids' rooms. So their rooms are still hot, but at least my streams got way cooler. So thank you. That was it.